Hello, everyone, fellow peers and professors. Thank you so much for being here today. My name is Shania Channon, and I am very excited to be sharing with you my final seminar for my master's dissertation. Before I formally begin, I'd like to thank my wonderful supervisors, Professor Simon Murphy and Shishir Dalokia. My project, as you can see here on the slide, is exploring the limits of transient outburst in cool edge ZZ SETI white dwarfs, which is an analysis of QLP test data. So just quickly before we begin, I'll go over a basic agenda for the talk today. We'll cover why this work is important in the astrophysics world, as well as the motivations for the work. I will follow with a bit more context and some relevant literature, and then we'll move into the research design and, of course, the results and implications. I do want to also just note quickly that this research is slightly different from the initial scope that we had planned. After a few rounds of deliberation and tweaking with the supervisory team and my thesis colleague, Aman, we decided to split the scope of the projects, and my initial thesis setting was shifted from looking at binaries to looking at the outburst behavior. So if you were here for the first presentation and wondering why the topic is slightly different, welcome to the wonderful world of iterative research planning. All right, let's get cracking. So why is this topic so important? Well, in order to frame this correctly, I might have to jump ahead a little bit and give you some background information first. So white dwarfs are the final evolutionary stage of about 97% of our stars, including our sun. So almost all of the stars that we can see in the night sky will eventually turn into a white dwarf. So this end process is both A, super common, and also B, super important to understand. Despite being the end product of stellar evolution, they are far from inactive or boring. One branch in particular, pulsating white dwarfs, are incredibly active, and their behavior offers us a unique window into their interiors through the study of astroseismology. So these pulsations, as you can see on the screen here, they look a lot like breathing, where the star expands and gets brighter, cools and then contracts and gets dimmer again. There are around 5 main physical mechanisms for this, and each mode of pulsation, duration, intensity is linked to a different mechanism. So depending on these parameters, we can infer the internal processes happening in the star when we observe their pulsations. Now, depending on the mass and evolution pathway that a star takes, you will get a few different types of white dwarf. So white dwarfs, as you can see in the first figure here on the left, they sit down the bottom left corner of the HR diagram. For this study, I particularly focused on the most common type of pulsating white dwarf, which is a DA variable, otherwise known as a ZZ SETI star or a DAV. These stars, as you can see on the second graph here, they sit in the middle of that white dwarf zone. Now, why DAVs in particular? Well, only recently, in 2015, by the work of Bell et al., which you can see on the screen here, an unusual behavior was observed in a subset of cool-edge DAVs. This behavior was a transient outburst. Now, usually, pulsations in DAVs and most other white dwarfs, they're pretty fast. They last a typical maximum of about 2 minutes, but usually around the 30 seconds, and a flux that increases of 1 to 2%. Now, this transient outburst behavior that was observed by Bell is a sudden brightening that lasts hours to days and can increase flux by 14 to 20%. These outbursts challenge our models of both pulsation and cooling, and to date only 6 have ever been found, and they have only ever been found on the cool edge of the DAV instability strip. Now, we need to go a little bit further. DAV stars occupy the hydrogen atmosphere or DAV instability strip, which you can see on the screen here. And it's defined between roughly 10,600 and 11,200 Kelvin. Pulsation in DAV stars are directly related to temperature. As a star cools, the convection zone deepens quite dramatically, and it allows for this development of turbulent modes that lead to a star pulsating, like we saw on the slide before, that breathing motion. The current theory around outbursts is that it's directly related, an extreme example of this intrinsic relationship. which is why they only occur on the cool edge. Only there is one problem. The exact start of the cool edge is still quite a debated topic. Some studies debate a hard cutoff, while more recent theoretical work argues that it's more of a transitional zone. So, by exploring the limits of the cool edge, we can better constrain where these pulsations and outbursts cease and why. It's not just a temperature boundary, it's a probe for the physics in the mode driving and damping. Okay, so now on to the fun bit, the actual project design. Firstly, we have to understand what the whole point of this research is. The overarching sentiment and point of this study was to explore the temperature range just outside the current accepted limits for the cool edge of the DAV instability strip. So that 10,600, 11,200 Kelvin mark that we saw before. And exploring that, looking for transient outbursting in the DAVs that we find there. This can be broken down into two key objectives. Number one, to systematically assess test photometry and search for outbursting cool edge DAVs. And then secondly, to evaluate the presence or the absence of this behavior and what that implies for both the behavior itself, so the outburst itself, and the boundaries of that cool edge. So, how do we do that? Well, the first step I took was to find some candidates for this study. There were two main options for this, either to explore an existing database of pulsating white dwarfs, or to take a bunch of raw data and try and find some new DAVs through photometric analysis. After a lot of deliberation, it was decided that the main analysis component of this work was going to be quite cumbersome in the outset. There was going to be a lot involved. So in the interest of time and, to be honest, a little bit of sanity, downloading from an existing database was deemed the more feasible option for this work. So there are a lot of different databases to pick from, but I chose the Montreal White Dwarf Database, which is run by a group of astrophysicists, and they collect data on white dwarfs that's been confirmed and published in literature already. So it removes that need to sort of verify whether this is even a pulsating white dwarf, whether it's a white dwarf at all. So in this database, you can filter directly on the site. So a first cut was done there. I asked for confirmed variable stars that are also DAVs. And this beginning search returned 3,053 stars. I did a secondary cut for this to limit the temperature ranges to either side of the limits of the cool edge. So what we talked about before, that 10,400 now to 10,600 for the first set, and on the other side, 11,300 to 11,500 Kelvin on the other side of the cool edge. A third cut was then done for magnitude. So as I decided to use test data for this study, tests can only reliably resolve targets under the 14 magnitude mark. So the candidates were limited to 14 magnitude and below. I chose to use test full frame imagery for this research, as QPL has a great full sky coverage and it's taken with standardized aperture photometry, which is a lot easier to process. Outburst behavior also lasts a long time. So like I was saying before, upwards of an hour at least, but can last for days at a time. So short cadence wasn't really a priority in this study, and QPL full frame was picked for this reason. It's also more readily available. There's a lot more QPL data than 20-second cadence data, and then would still be able to resolve an outburst. So the Montreal database collates targets across hundreds of published studies, and they all use various missions and instrumentation to capture their data. So in the original download, they were all sort of different names. They were either had Gaia numbers or two QPL numbers. So for the final cut, I wrote a cross-check function in Python to look through both MAST and Simbad and check whether the original name that the database gave me also had a tick number, a tick ID. So that confirms whether it has coverage by TESS. And then a secondary search to confirm whether it has QPL sectors that have even captured the target. So after these cuts were made from the original 3,000 or so, I ended up with only 46 targets that qualified for the analysis that met all of these criteria. Now, the next step was to actually create the algorithms needed to detect the outburst behavior, which was the tricky bit. We've already talked about the cross-check here, so I will skip to the main component. Since this was a fairly recent branch of discovery and analysis, there wasn't a lot of resources to assist with this portion of the study. But two researchers, Clark and Kawela, last year published a paper that detected 2 new outbursters, and they also made their code that they used for that open source. So I took that as a base model, and I made some additions to that. So I integrated a GUI component to make it more user-friendly, and then added 3 key analysis steps. So the logic behind that was to create multiple validation points within this pipeline that I was building to limit the amount of errors that I received. Behind the scenes, before you saw analysis pop up, I had put in functionality to search for all the QLP sectors and the target appeared, to then clean the images for any non-data, any NANs, and standard noise, normalize the curves, and then perform a sigma clip. I just used a standard 5 sigma threshold for this, as that's kind of standard across the literature for this type of work. So then this is the analysis. It moves from that background work to this analysis stage. And like I mentioned, it goes through 3 phases. So first, a light curve is produced to visualize pulsation behavior. I've got examples of the real targets that I was looking at on the screen here. So the first step is that light curve there. So you can visualize the flux changes across all the sectors, and you can just kind of visualize any abnormal features that pop up. From there, if the pipeline identified any peaks that exceeded the sigma threshold, it flagged, and then it moved to the next stage, which was a Lomsgagel plot. For this, I did choose a window function for this instead of a typical plot, as I wasn't trying to identify the peak's wavelength, but rather if the peak was an authentic signal or whether it was more attributed to noise as a fail-safe mechanism. So this was less of a diagnostic tool, which is why I went for the other option. After this, a waterfall plot was produced. And again, this was to verify and validate pulsation behavior and any peaks that were deemed significant. So it was more just to make sure that what I was getting in the light curve was authentic. A significant peak in this whole process could only be quantified and flagged as an outburst if it reached the 5 sigma threshold. So if that was exceeded, and then if the peak sustained above that mark for more than 1 hour minimum, and then if the flux change above that mark exceeded 2%, which was the lowest level quantified by previous work done in this field. So after that, I built a final function, and this was an actual diagnostic tool for analysis, which was based off previous outburst work by Hermes in 2015. So the way that they did that was when they found an outburst or what they believed to be an outburst, they would take the time immediately before, during, and after the event, separate it, and then perform a Fourier transform on each of those, and then layer them to gauge whether an event is in fact an outburst or just an extreme pulsation event. So, what did we find? Well, of the 46 qualifying candidates, there were 260 sectors of QPL data across the board, and each of those were analysed. Across these, there were 183 significant peaks, which is quite a lot. And of those, there were 2 in particular that were identified as outbursting behaviour. Now, the big question was, were they valid? Were they real? Unfortunately, no. So TIC 779-66679 was our golden child of this study, and it displayed 2 significant peaks, one in sector 3 and one in sector 12. And both of these were flagged as outburst behaviors by the pipeline, by the algorithm. So peak number 1 that you can see on the top here had a duration of 7.67 hours, about the sigma threshold, and a flux change of 1.7%. So that's a little bit under the limit that we set. However, its shape, it was flagged and the shape is pretty steep. So we kept it in. Peak number 2 lasted for 9.43 hours above the threshold with a 3.7 flux change. And as you can see here in visual inspection, it is these outbursts that have been flagged, they are, they're dramatic, but they look as part of the normal pulsation. They aren't complete visual outliers, which was the first red flag. However, they were flagged and they met the limit, so we went through with the diagnostic code anyway and got the result that you can see here. So this is based off that work by Hermes in 2015 and following the analysis they did to verify their outburst behavior. So ideally, in an outburst event, you would see a really dominant in-outburst peak on both the light curve above and the stacked transform below, where the pulsation behavior for pre and post outburst would still be visible. You would still see those fluctuations, but they would be much lower on the amplitude scale that you see on the bottom there. So what this result in particular is telling me with the large post-outburst and also the large pre-outburst is that the peaks that we found that were qualified as outbursters, they're significant, but the overall pulsation behavior of this star matches that peak. So you have this rather dramatic pulsation that goes a little bit above and beyond what it usually would throughout the sectors, and that these are slightly larger peaks, but they're really just slightly larger pulsations rather than outburst events. Bell himself, actually the discoverer of these events in 2015, states that while the lowest limit of an outburst is a 2% change in flux, which these exceed, but it is rather common for a peak found under the 5% mark to just be extremes of usual pulsation behavior rather than an outburst event. And unfortunately, that is the result that we got here. So where do we go from here? Well, firstly, I'd like to just talk about a few lessons learned from this work. There were some overall errors in the pipeline that were made. Test data in particular, which is what we use for this study, is known to have a few systematic imaging artifacts. And while the algorithm was built with a lot of data cleaning and normalization, the final stage of that was sigma clipping. And that was the tactic most used for this purpose, which led to some sectors throughout the whole data set having these imaging artifacts come through in the graphs, because the cleaning techniques that were used weren't specific to the test instrumentation. An example of that is given on the screen here. You can see that sort of zoomed out, the main graph stays quite stable around that one flux mark, but then you have these really symmetric, large, almost outburst-like events, but they're not the usual characterization. They're not the usual shape of any sort of pulsation type. And so these are actual artifacts of the instrumentation of tests. These appeared in a few sectors throughout the whole data set, and where they appeared, they also skewed the Lomsgargles and the waterfall plots. So this actually carried through on the additional analysis that was performed because it's registering as a peak. It's not a huge issue, as significant peaks could still be resolved even with these in there reliably in the first step in the light curve, but it does limit the validity of the other two plots if you want to take the analysis further. So if you had a significant peak in the light curve, but also one of these artifacts, and then you wanted to get information from the periodogram or the waterfall plot, it would still resolve a result, but you would have significant side lobing and significant noise in those plots because of these artifacts. So in the future and future studies, The test-specific cleaning method should be integrated if you were going to be using that data to avoid this issue, to clean it up a little bit. The null result on a whole, while a little bit disappointing, it speaks to the rarity of this event. And given new data is obtained every day by missions like TESS, I would suggest that future work expands the scope to identifying new DAVs from raw data before using a similar pipeline to the one that I used, just to cast the analysis net a bit wider, just to improve your chances of detection. 46 candidates from 3,000 is not a lot. So these are quite stringent parameters we are trying to work in. So casting that net wider will improve the chances greatly. This result also serves to reinforce the current limitations that we have for the Coolidge. It hasn't disproven that it's the current limitations of that instability strip, though I do believe if a larger scale study was performed and structured in the same way, it would be very useful for the progression of the field overall. In conclusion, this work helps to constrain where and how pulsations die out at the Coolidge and highlights the rarity of these events. They're very hard to find. Ultimately, if we were to refine the detection methods a little bit and expand the samples, I believe the structure and the intention of this study both would help move towards answering one of those key questions of astroseismology. This is a really exciting new field that's come out, and I think it would benefit with a larger study. Thank you so much for listening. If you would like to talk more, or you have specific questions, or you would like access to the code for your own study, please feel free to contact me via the email here. I hope you all have a nice day.